The first thing to be said uh, is what I'm looking for, right? I'm looking for a kilonova most of the time, right? Gravitational wave counterparts are nowadays a hot topic. People are very interested on that. And I'm mostly searching for kilonova. So first of all, I would have to say, what is a kilonova, right? Kilonova is a process where you have a merger between two neutron stars, okay? Is expected to be accompanied by a short gamma ray burst that might be visible or not, depending on the viewing angle you are from the kilonova. During the merger, there's a lot of things, a lot of astrophysics going on. Some of them are not well understood. There is a lot of ejecta. There is R process, rapid neutron capture process that enables us to create heavy elements like lanthanides. There are X-ray emission. So a lot of things going on. We expect to first have a blue emission, and later on a redder emission in an afterglow, and so on. So the observations of kilonova can come over from the radio up to gamma rays, and they enables us, together with LIGO, Virgo, and the other detectors, to actually do multi-messages in astronomy, right? That's one of the most interesting things to be seen, right? Let me go over here. So, but why should we bother on looking on this gravitational wave counterparts, right? And especially kilonova. Well, up to now, we only have one confirmed counterpart, which is known as the W170817. You get after some point, you get used to know gravitational wave events by name, which is a little bit weird, but it happens. So the W170817 was the most famous one, which was the one that was found after a couple of hours, a gravitational wave counterpart. This is a neutron star merger. Well, as I mentioned, the interesting physics is around what's happening during the merger. Does the magnetic field plays an important role on the process or not? What's the amount of heavy elements that being produced inside this kind of mergers? How rare they are? These are a lot of open questions that we don't fully understand, right? Um, the geometry of the ejecta and other effects. Okay. Also, as I mentioned, it is also an important way of understanding the creation of heavy elements, right? So if you see, this is what we learned after JW 170817, which is most of the sort of heavy elements are produced inside this kind of merging. So it's a rare phenomenon. However, it's important to understand how the elements are produced, especially on lanthanides, right? So the lanthanide fraction is an important quantity. If you look at this table, you might be a little bit surprised with a lot of gold. Most of the gold in the universe is done over there. So as I'm in Argentina, I should mention also Argentum. So uh, La Plata is done mostly inside this merger, which makes Newton Star merger maybe a Argentinian event, right? So moving on. So we don't fully understand. We have only one confirmed gravitational wave kilonova. There are several other candidates. Earlier this year, there's been a claim of a novel kilonova, which I participated over the process, but it's still open questions because we don't have gravitational wave counterpart over it. Okay, so uh, here we go. Another important thing, and that's why I turned to this field, is the Hubble tension. So as you might be aware, cosmologists, and I put myself among them, are very confused about a lot of things, right? Most of this confusion might be related to systematics in our probes, or just because, well, the standard cosmological model is very simple. Okay, so one of these main tensions is known as Hubble constant tension, and it can be seen by this plot. It's not really up to date, but it's very didactic. So what we see is, we have two kind of measurements, one from the early universe, an indirect measurement, mostly dominated by CMB measurements, and the recent universe measurements related to Cepheids and supernova 1A. Okay, these two kind of measurements. Let me see if this works. I'm not sure. Oh, yes, it does. These two kind of measurements of Hubble constant, they've been moving in different directions. So if you see CMB related measurements go to a low measurement of the Hubble constant, while the supernova measurements more or less go to a higher values of H naught. Okay, so one of the things that could, in principle, solve this issue is gravitational wave standard science. So here is the first measurement, as I mentioned, the famous event, the W17 or 817, and this is a sort of forecast of what could be done in a couple of years from now. So the main issue is find those things, because well, gravitational waves are the gravitational wave observatories only give you not precise position on the skies, so you have to search for it and find it an event which is not always will be as bright as we would expect. So we aim that at some point we could have reached the precision. The golden number here is about 2% precision, where we could finally make an arbitration between these two different measurements. Okay, so that's one of the things. So as I mentioned, what does LIGO-Virgo, now KAGRA and others, and future LIGO India do? So they are very good at identifying these compact mergers, okay, at cosmological distance. They are good at this. They can detect binary neutron stars, binary black holes, neutron star black hole mergers. Okay, so this one, the binary neutron star mergers, they have no afterglow, no kilonova. You observe it at least once. The neutron star black hole pairs should have afterglow, probably much redder, but still an afterglow. And binary black holes, which is not likely to have, but maybe. Let's see. So they are also good at measuring cosmological luminosity distance, which is good. So we use the distance measured by them, and we need to follow up in the skies and to find the cosmological redshift. With the redshift, you can derive distance log distance measurement, and then you can check and find your cosmology. So that's the idea. You compare two measures of distance, one for gravitational waves and one that comes using the redshift. Okay. So the issue is there's 1,000 square degrees in the sky to look at. Okay. Just a few moments before this seminar, I just received another alert for an event with hundreds of square degrees to be searched upon. Right. So that's the thing. If we find it, we can use it as we call standard science. Okay. So we have this, as I mentioned, neutron star merger observed once with gravitational waves, but likely a couple of times more with short gamma ray bursts or long gamma ray bursts. Neutron star black hole mergers never observed, and this, which is, well, it's a completely unknown field. Okay, so what we would expect the next years in this field is, well, at least to find new neutron star mergers, and to see if we can make a huge discovery of a neutron star black hole. Okay, so how does this work? As a matter of fact, so we have the decision makings part and evaluation. What the event starts, there is an alert from LIGO. We all get a little bit nervous. There are several groups with access with different telescopes. So in my case, I'm part of the one of the DECam team, the DSGW team. I also have access to the T80, the telescope from S-PLUS, to make this kind of search. And so we all get together in Zoom or at some point It can happen during the night, can happen every time. Um, and try to decide, are we following this up or not? The reason is simple. Some events might be too far away. Some events are simply not expected to give electromagnetic counterparts. There is a very limited time because you need to disrupt everything that is being done in the telescope. You have to lock the telescope and say, point to this direction right now. Okay. And as I will mention to you, this also needs to be fast because the event fades very quickly, different from a common supernova that maybe be observable for months. Here you have a couple of days, okay, maybe an hours, depending on when you start. So we have to set up an observing plan. This should be very optimized for the nights you're looking at. There might be clouds, there might be a lot of stuff going on. uh, Once we decide to follow up and to collect the data, we have to lock the telescope before others because maybe there's another group trying to lock the telescope. So if you want to use that facility, we need to make the decision as quickly as possible. After that, on the sky, single epoch image is done. There's a verification of the data, reduction, and so on. Difference imaging. When you need to find transients, you need to do difference image, which means I need to have a previous image of the sky of that specific part. Okay. So you have the search, which is the night observation, the template, the previous observation, usually deeper, and maybe from another telescope. And then you have to make the difference image. This process, well, lots of things going on, and many things go wrong while doing this. You can imagine you have image with different noise levels, have artifacts, have misalignment. Everything must be done during the same nights because we have to make a candidate selection that go for spectroscopy. That also is target opportunity. Also, you have to lock the telescope and be prepared to receive this. Well, a lot of things can look like a kilonova because a point source. So it can be a variable star, can be an asteroid passing by. So we have to ask ourselves, is this an asteroid? Is it a variable stars? Is this an event that doesn't make sense? Because as we have the velocity distance from LIGO, maybe the photosys is too far away. Maybe we don't have photosys. Everything can happen during the night. Okay. And after the cyber attack that recently happened to many of the telescopes, there's also issues with connections that we find out in the middle of the night. Okay. I think I made my case and how difficult this can be and how messy this can be, especially because everyone is super tired doing this. So the strategy is an important thing, important part. So this is an example of event strategy. Of this red, white lines here, an example of the banana shapes from LIGO, where the gravitational wave can be, the counterpart can be. This one is the pointings that we are doing during the night, and this is the night passing by. Okay, so if the event happens to follow over the galactic plane, it's hard. So you should observe. So many things can happen. Okay, and you can see the big parts of the sky, and they do this banana-like shape. This is also the DS parts of the sky because that's a well-covered part. We have good templates over it. Anyway, so when the LIGO star dollars, we have to decide. It's feasible to find. How are you going to find? How is likely for us to find? That's the three questions we need to ask. And I did a whole paper, a DS paper about it this year. Okay, so this is DECam. I mean, not the real DECam. This is the prototype in Fermilab. And this is another kind of pointers. So we have to lock the DECam, and we do this remotely with the teams in Fermilab, with the team in Brazil. We all do this together. There's a team in Chile, everyone working connected. This is the observation room site Fermilab with some of collaborators, Sahar and Douglas, and we have to decide this. This is an actual CCD from DECam, right? So this is DECam is full with these CCDs. This is just a prototype that was done in the lab where I was a visiting scholar at Fermilab. So this is the DECam for real. Okay. So as you might know, DECam is a very good instrument to do this search, and I'll make the case that T8 is also good. The S-PLUS telescope is also good. So it's 570 megapixel with 3 square degrees. Okay, field of view. So you see the moon over it. So we also we observe remotely, both with DECam, people observing, and we also observe with the spectral parts. So I'm currently the PI in the SOAR proposal from Brazil, where we make the target selection. So I think I made myself clear that everything is done in the single night, including the reduction on the spectroscopy. So that's the crazy part. You have to reduce, make the data reduction and classify the object, because otherwise it might be just too late in the next night. Okay. So what happens in a real observation? Well, we are most likely not to find, as you would imagine. Okay. So this is one of the events that we followed up, level 190814. It's a very well localized event. As you can see here, these are the points from DECam. This is the different images, some examples over it. However, even if you don't find it, we obtain a lot of data, and we can understand a little bit more and make constraints on the physical properties of the kilonova. Okay. So in this event, it was a very well covered event. You can see here some points. These are the transients we discover over the night. Okay. Well, that's only transient that survived our cuts, as a matter of fact. We started with the 30,000 transients in the sky. We have to reduce over to 15. Okay. And then 11 were actually observed by SOAR. Okay. One of them couldn't be observed, but was a wrong identification. Anyway, so we have these detections. This is the magnitudes. We have more transient as the magnitude goes up. We have to detect it twice to eliminate moving targets. You eliminate it by photo Z if you have it, and then you have to look at the images to see if it's nothing just weird. Okay. And also, this is the first night. Okay. A little bit later, LIGO returns a different map because they did a most precise processing, and then the map shrink. What happens? We find objects that are outside the region, the confidence level. But that's life, you know. The night we observed it, that were the region, and then the region got a little bit smaller. Okay. So this doesn't mean that we don't find interesting stuff. We find a lot of supernova. Okay, and we have to fit them to see if they are likely kilonova or supernova. Okay, so this is the best fitting for a kilonova. As you can see, it's not a kilonova. The best fitting for a supernova. Okay, this is the photometry obtained. This is another event where we could only observe the host galaxy because it was just too faint. Three candidates, they become too faint for SOAR when we start observing. There was this one that was an interesting event and missing candidates. However, it does look like it's a fit for a kilonova, right? But if you look closely, you see that signal to noise is just too high. You can make a point of being a kilonova. Okay, that's what happens with this one. And we also use photometry to show that it's not a kilonova. Okay, even though we are able to make some constraints about the ejecta mass, the velocity of the ejecta, and the non-light fraction. Because we would know if as we know that the deep how deep we go with the camera, we have kilonova models. So if we don't see it, you know, it should be fainter than what we could see with the camera. So you can make constraints over what is would be the kilonova models that are unseen, that should be unseen by us. Okay, that's the thing. Well, then we realized after the last campaign that we are not using the best strategy. We should think a little bit harder and how to define a best way of looking at this region, because you have to cover everything fast and you have to make quick decisions. So what we did is, well, we have to define a optimized strategy. But how do we do this? That's the hard part, because we need good models for it. And well, we only observe it, as I mentioned several times, one counterparts with gravitational waves. And it can be neutron star, neutron star, neutron star, black hole. So everything can happen. We actually don't know exactly what kilonova look like, especially because of the viewing angle. The viewing angle can change a lot of stuff, because well, you see a redder component in some direction, you see a bluer component in another direction, for instance, right? If the neutron star black hole, you won't expect redder components. Other thing is what will going to be the output of the merger. We don't know. Can be a neutron star or can be a black hole. Okay, this will give you different properties on the merger. Okay. So what we did, for the best of our knowledge, use the Kaysen models. Is an for a Nature paper, and we did light curve simulations, a lot of light curve simulations with SNN, with a known light curve simulator. Okay, and then we start putting DECam and simulate observation with DECam. How? We explore a very big a big set of parameters. So the cadency, when are we observing? 12 hours, 24 hours, and so on, until the day number 4, with all these filters covering. We can cover the whole area, you can cover a smaller area. The trend is, if you cover more area during the night, you need to be shallower because the time is finite. Okay, so that's the trend. If you cover the core area, which contains the more probability of hosting the kilonova, you can, for instance, spend more time and go deeper in that region and shallower in the region where there's lower probability. That's one of the things. So we tested several filters, and depending on the night, is the night is clear or it's dark or bright, for instance, or gray. So we did all these tests to calculate the probability of finding the models. Okay, and not only find once, but twice. As I mentioned, we have to find it at least twice. Okay, to be sure we are looking at the right thing. So this is the discovery probability and the telescope time required to cover it. Okay, for the first observation, and this is a total observation. This is a single event. All right, as you can see here. So this is the discovery probability for a single event, and in the second pass, because the event starts fading, right? So the probability of finding the second pass is not the same as the first pass. The second pass and the first pass, and this is correlated by the total telescope time. So that's the top strategy, which uses more telescope time, and there's what we optimize for lower telescope time, is you have significant probability of finding, around 70%. Okay. So what we discovered that the previous strategy was not very good for a very far away event. Okay, if you consider a kilonova like GW17 or 817, because you need to define what kilonova you're looking. Okay. So for faraway events, we need to optimize the strategy, like the code they're producing can provide. So that's the thing. But the kilonova might be very red, very faint. So this is the previous strategy, the probability of discovery as a function of distance. And this is the previous strategy that falls down very quickly. And this is the optimized one using DECam. So it's very faint. It's sort of like what we would expect for a neutron star black hole merger. That's what you got. So with the optimized strategy from the code I worked on, you do as good as 50% at the limits of LIGO observations. Okay. And when I mean the limit of LIGO observations, I mean what will be like if LIGO, Virgo, and KAGRA were working as expected, which they don't right now. Okay. So I'm going to skip a little bit ahead because I'm kind of running out of time. So the takeaways of this paper is now you can know the probability of finding an object that are in this luminosity distance thing covering with this area in the sky from 25 square degrees to 225 square degrees with these probabilities. Okay, and you need, in terms of DECam, this sort of time. So less than an hour for a very well-localized event, something like 4 hours in very badly localized events. Okay. For another kilonova, things get messy. You don't see very well. This is, again, the luminosity distance beam and the area in the sky beam. Okay, so and you spend way more hours. So for a very red kilonova, you can spend up to 14 or 15 hours, which is a lot of telescope time to be interrupted. Well, as I also mentioned to you, what happens if we don't find it? Well, you can get astrophysical constraints, but you can also get cosmology out of it. And that's what we did. If we don't find the counterparts, you can use what we call the dark siren, okay, method. Dark siren method relies upon an idea where you don't localize the galaxy, but you can consider a probability of every galaxy in the field to be a host of your event. And then you marginalize over the whole catalog. So the catalog must be as complete as possible with the photo Z as good as possible, which is not always the case. However, we were able to make this with the 3 seasons of observation from LIGO and the legacy survey. Okay. So what we got here is the precision of the bright standard siren, which is GW17, the only one confirmed with the host, where you could reach a precision of H0 of 80% with a single event. Okay. So we use 8 dark sirens to reach a similar precision. What we show is if you have 8 well-localized dark sirens, you can do as good as 1 bright siren, which is reasonable. If you combine them all, you are reaching 12%. Okay, precision on H0. And this is our posteriors. You can see the Planck and the Adam Rees paper from 2021. Okay. So we are getting there. We are getting there at some point. Okay. The other thing my group is working on furiously, is trying to define if BBHs, binary black holes, are able to produce or not visible counterparts. So the rough idea is that a merger of 2 BBHs, 2 black holes inside an AGN disk, they can bring a lot of material together, and they can make a bubble over the AGN disk. Okay, and after the merger, they get a kick. They get kicked out the AGN disk, and together with them they can make an outflow here, and this would be observed as a flare. So the AGNs can flare if they host a BBH, a binary black hole merger. Okay, I'm not talking about the supermassive black hole inside the AGN, in the center of the AGN. I'm talking about two black holes inside the AGN disk. Okay, so this paper from a postdoc working under my supervision discuss exactly this possibility. Okay, there is another possibility depending on how the geometry of the process and the mass of the black holes involved. This will give us different flares that can happen in the ultraviolet, can happen in X-rays, or in optical, which is the one I'm most interested in. Okay. So can we make cosmology out of this? So that's my next question, right? So if the mergers happen as we would expect, this would enable us to use binary black holes that are way more abundant to make standard-side. Okay. However, it's really hard to know if a flare is or not from a BBH, just because AGNs flares all time, okay, and they have a variability. So you need very good models to do this, or you can simply assume that there will be some flares related to normal variability of AGNs, and some flares that are just going to be that are going to be from BBHs. You can model it in a Poisson process to try to identify and get cosmology. This is one of the topics I'm working on right now. Okay, and then this can be huge in the sense that between 80% and 20% of the BBHs are likely to happen inside AGNs. Because some people say, "Oh, okay, you're looking to a very rare stuff." Not exactly. The AGN disks are a good environment to produce BVHs. Okay. All right. So what about S-PLUS and how this relates to people with access to S-PLUS, right? I know that Argentina also has an initiative to find these gravitational wave counterparts, right? But we are trying to use S-PLUS to do the same kind of stuff we do in DECam. Okay. So S-PLUS is a very nice resource to it because it's also a wide field, and we need wide fields to find counterparts, right? It's not as big as DECam. However, in DECam, that's very small amount of time to do this. That's a good thing. To do this, we have to implement everything for TAT. We have to build our own pipeline, of course, based on the other known pipelines, but for TAT. Okay. So Andres Santos, a PhD student working with me, is now one of the observers of TAT or S-PLUS telescope, and he and Charles Kilpatrick, a good collaborator of mine in the US, they produce this pipeline to work exactly in TAT. So we have the similar structure as we do in DECam. Everything is pretty much done right now. This is already on submitted. Okay, and so the idea is, again, reduce the image during the night, get everything done. This is done inside VPF servers, and we have to compare with template image. Here things got more and more messy than it was in DECam, because in this scenario here, well, the template is usually a DECam image. So you compare TAT with DECam. So different telescopes, different resolutions, a lot of things going on, okay? Well, but we managed to do it, right? I'm just, as I'm going very far in the time, I'm just skip a little bit this. So this was actually the first supernova seen in S-PLUS data. Okay, so we made a difference image. So this is the template image from DECam. This is data from S-PLUS, and here's the difference image. So we not only are looking for gravitational counterparts, but we use the main S-PLUS survey that happens every night. We download everything to CPPF servers, and we compare two templates to find supernova. Okay, that was the first one we observed. Okay, and this is the first one discovered by us. This is the first supernova discovered by S-PLUS. I know, just a bright spot, but for us, it has a lot of feelings about it. Okay. Well, how T80 can be useful? It's very hard to have high cadency for light curves, and this is very important to some constraints on supernova science and some constraints in kilonova science. So that's the good part of, as you can see, the fits are not really working well in the in after a long time. So we need more resolution, and we need resources to do this. These are rare and hard to find. So T80 can help with that. We are currently studying this supernova. Is a type 2P supernova. Okay, and so we can probe, as we have the previous imaging from Hubble and other data prior to the supernova event. We can even probe what was the late stage of this star before it became a supernova. So we can fit. This is a parameter fit for the supernova model. This is a work done for one of my PhD students. You already did this with another long supernova in Davis et al. Already published. This is a very interesting one where we use high resolution in the afterglow where S-PLUS data was really useful. Okay. As you know, it's very hard to understand the difference imaging. So here you can see what we see during the difference imaging. I should have mentioned this before, but many times we are during the night looking at it and say, "Oh, this is a real object," or "This is not a real object." So two of them here are real and one is not. Which one is the real? So this one is a bad subtraction. It's very hard to spot with our own eyes. It's very easy to be misled. Okay. So what we do? Well, another student of mine working on a CNN to actually classify this as a real transit or not, so we don't look at everything all the time. Okay. He did this for DECam, and he did this for S-PLUS. So these are implemented, it's working right now. This is the the completeness by false positive rate. This is the purity against the completeness. A perfect classifier is around here and here, okay, in this curve. We have reasonable results. So the confusion matrix is here. So this is the correct classified transit, and this is the missed one. So we are okay most of the time. So we already observed with T80. This is one event we covered. This is the point of what we did. So the pipeline is working. T80 is ready if they allow us to use the telescope to do this. Okay. And I use the same algorithm that I use for DECam and explore similar parameters to produce the same kind of curve for T80. And it does pretty well for a bright kilonova. Okay. So that's what it does. Okay. This is the first and the second pass of the telescope. So what's expecting us? Well, my takeaways right now, I already talked too much. So I don't expect personally, and I think many people don't expect to have kilonova as bright as it was or as close as it was 017 or 817. So the next kilonova to be seen are going to be harder at least. Okay. We can optimize the strategy, as I showed you, okay, using simple algorithms as the one I created. There's a lot of areas to require improvements in difference imaging, remove artifacts, and people are needed all the time. If you don't find it, you still get H-naught. That's a good thing, okay? You only need more events and complete catalogs to do this. And we can also explore the AGN counterpart possibility. This is an old forecast we did just to give you a rough idea on what it will be like in the future. So we hope that we get the precision of the 2% precision around here. It may happen soon as 2030 or maybe as later as 2042. Hopefully sooner than later. You'll be hearing from me the Hubble constant issue being solved or for others, right? So my final take-home message is, well, there's a lot of interesting transient science to be done. There is an object that never been seen before that can be discovered. Okay. Well, I don't know, but I hope to have this answer. Do black hole mergers generate agent flares? Hopefully, there are a couple of candidates. How are these black hole neutron star mergers? We don't know. We only have theoretical models for it yet. Well, there are other transits of interest that can be observed with the T80, like strong supernova, and so on. Things that are interesting to work on. And I'm in fact working on this in LSST. Computer science stuff to be done, and a lot of follow-up research to be required. Well, that's what my take-home message. So thank you very much.